minus d, and this is often 0. So one of the things that people did when studying curves is to study the canonical embedding. So this is more or less from the time of Riemann's immediate students. So for example, if genus 3, then Kc has degree 4, and L of Kc is 3, and so this gives you a map from C to P2, and you could hope that it maps to isomorphically to C in P2. Right, and there's exceptions to this, which are sort of famous and everybody knows about. Right, so if you have this ring, if you have this embedding, then you have a ring here, which is K, X0, X1, X2. So this is the homogeneous coordinate ring of the projective space, and the C4 is defined by one equation. So this, the homogeneous coordinate ring of C is this thing here, divided out by principal ideal F4. Right, and the point I want to make here is that if you take the entries in this ring, the elements in this ring of degree 2, you get H0. So L of D from now on is going to be H0 of D. So this is, I get H0 of D. So if D is 2K, I get H0 of 2Kc. And now use this formula as given, and it tells you that you get 3g minus 3. You get 6. This is a 6-dimensional vector space. And so this thing here is something which is intrinsic to the curve, whereas here I have the part of this ring in degree 2, which is x0 squared, x0, x1, x2, x1 squared, and so on. Right, or if you want, this is the symmetric square of H0 of Kc. Right, and so the idea I want to pursue here, and the idea that's been most of my that I've done most of my career, is to look at the ring of C and Kc, the graded ring. So this is H0 of, I take not just Kc and 2Kc, I take all possible Kc, and I take the direct sum n greater than or equal to 0. So this ring here is a ring that's defined intrinsically to C. The multiplication in the ring here is just multiplication of rational functions on C, but it corresponds to putting the thing into an ambient space and asking what its defining equations are. Right? And so I used already Riemann-Roch here to get out this number 6. Right, and let me just pursue this idea just a little bit further. So if I look at this ring RC of Kc, then in degree 0 there is the section 1 only. In degree 1 I have H0 of Kc, and so there are G sections here that I probably want to call x1 up to xg or something like that. Right, and then in degree 2, I have H0 of 2Kc, and the number I have of these is 3g minus 3. So that's this number. It's 1 minus g plus twice 2g minus 2. Yeah, and in general, in mKc, I'm going to get, sorry about this, 2m minus 1 times g minus 1. Yes? And so this study of this curve here, I already said that there's a coincidence here that this H0 of 2Kc is 6, and at the same time there are exactly 6 quadratic forms, quadratic monomials here. And in the lucky case, this is a basis. If you calculate this also in degree 3, you'll notice there are 10 monomials of degree 3, and you'll notice the Riemann-Roch formula gives you 5 times 2, which is, again, 10. And then in degree 4, you get one equation by the same thing. So there's a game here of counting monomials. So, you have to learn to count, and you have to learn to do this calculation inside out. But I'm going to skip it. I'm going to skip it all and introduce this notion of Hilbert series. Right? And so suppose I try to put all of this information into just one piece. Right? What I get is this. I'm going to write P, so this is a function of this ring of T, and the ring itself is a function of C. So I really want to think of this as PC of T. So I'm going to write this sum of Pm T to the M, so T to the M. Right, so this is the dimension of this vector space, H naught of K M Kc. Yes, and so this is a power series that is 1 plus gt plus 3g minus 3 t squared plus 5g minus 5 t cubed plus and so on. Yeah, and the entries here are given by a kind of formula, polynomial formula. In this case, rather easy, linear formula. Right, and the result of that is that this guy here is not just an arbitrary rational power series, it's a rational function. In fact, it's this thing here you can calculate is 1 plus g minus 2t plus g minus 2 t squared plus t cubed over 1 minus t all cubed, all squared. Yes? So some of you might have seen me do this, derive this formula. To derive the formula, what I do is I take this expression here and I multiply it by 1 minus t by long division. So when I multiply by 1 minus t, I get 1 plus g minus 1t plus 2g minus 3t, and then from that moment onwards I'm just getting a power series which goes on forever as 2g minus 2t cubed, 2g minus 2t to the fourth, and so on. Yes? And so I'm differencing. I've got a polynomial here, happens to be a linear polynomial, and I'm differencing it. I'm taking it minus its value minus 1. Right? And that simplifies the expression. So if I do this 1 minus t again, what I get is this. Yeah, so for our buddy here, I'm getting 1 plus t squared plus t cubed plus t to the fourth divided by 1 minus t all squared, and I can, I'm sorry, I'm rushing ahead, and I can simplify this in a way. I mean, you know how to solve this as a geometric progression. So this thing here is 1 minus t to the fourth divided by 1 minus t all cubed. Right? And I can think of this 1 divided by 1 minus t cubed as the Hilbert series of the projective space. Right? And I can think of the 1 minus t to the fourth as saying that the monomials on c to the fourth are the monomials on p squared, on p2, minus those that are multiples of the equation of degree 4. So, I mean, when you need to have done a bit of practice at this, but when you see an expression like this, you think of this as being the generator of the ring, and this as being some kind of indication of what the relations in the ring are like. Right? And so, I mean, I'm only talking about the numerics of the canonical ring. The canonical ring of a curve was studied by Brill and Noether and Petri, and there's a lot of stuff known about it. There are still people who spend their entire lives working on this kind of thing. So this is I'm only talking here about this numerical function of the curve. Right? And so here I'm using Riemann-Roch. The basic thing I'm using is this expression. Right, let me do some surfaces. So so the hyperelliptic curve, I have to write 1 minus t, I have to 1 minus t squared. I'm sorry, I have to write 1 minus t cubed, 1 minus t squared, 1 minus t to the fourth, 1 minus t squared. So in this case, it so happens, so as Young-Nam is saying, the thing I said here was an oversimplification. It might happen that it's an isomorphism to a curve in C4. However, there's an exceptional case. There's always an exception in any good story. So the exception is that this maps 2 to 1 to a quadric, to a conic curve in P2. Right? So that means that these 6 monomials in this space, H0 of 2kc, are not linearly independent. I have 6 elements in a 6-dimensional vector space. They're not linearly independent, so there's a relation between them. That relation is the equation of the conic in P2, and then I have to add in a new generator. At the same time, I get a new relation. Right? So there's the equation of the quadric, and then there's the equation of the double cover of the conic, which is this y squared appearing twice. So, I'm, of course, grossly oversimplifying. I'm trying to get into the general higher dimensional case. So I think everybody knows Riemann-Roch for surfaces, for divisors on the surface. So S surface, so, as exactly as before, I'm not writing down the definitions. Non-singular projective surface. And so it has a divisor on it called the canonical class. If I want to know, I might want to know about H0 OS of D. So I might choose a divisor and say, how many sections does it have? And so when you're wise, you don't ask immediately just the question about H0, you ask the question about chi OS of D. Right, and the formula is, I hope everybody knows, chi of OS. So this is just some constant. We'll have some words to say about it later, but at the moment it's just some constant plus 1/2 of D into D minus KS. And basically the most important thing about this is that it's a polynomial in D. Right? And so already just the fact it's a polynomial in D and the term D squared appears in it already tells you most of the geometry of surfaces. So it tells you, for example, a Hodge index theorem. So, if you haven't got this in memory already, then please commit it to memory. You need it all the time. Right? So I want to assume that Ks is ample. Or later I want to assume that Ks is some multiple K of an ample. And then I want to say, what happens if I do D is the same as here? D is M times Ks. Or more generally, M times A. But let me just do this case for the moment. Right? And so, you can ask, so I'm assuming Ks is ample. And so this means that there's a kind of little area of uncertainty. So here, L of D, we don't know. Right? So that's exactly the same as for curves. Once I get past K, so if I've got, so the thing I'm trying to say here is that I'm going to draw my little table here, value of M, value of H0 of M, MK, right? And when M is 0, I get 1. When M is 1, I get PG. And that's just the definition. PG is the geometric genus is H0 of Ks. And then when I'm greater than or equal to 2, so M greater than or equal to 2, the number I get here is chi of OS plus M choose 2 times K squared. Right, so it's m times m minus 1 times k squared, and then all divided by 2. So it's this number here, binomial coefficient m choose 2 times k squared. Right, and so again, this is a polynomial in m. So if I write p, sk of t to be sum of these pm's t to the m, right, then taking this guy here and multiplying by 1 minus t is guaranteed to simplify this expression, because so this will be sum of pm minus 1 t to the m, and that first place kills this term, and the second place replaces this m choose 2 by m choose 2 minus m minus 1 choose 2, which is a simpler expression. Yeah? And the answer you get, if you do this 3 times, the answer you get is 1 plus chi minus 4 t plus k squared minus, let me think about it, t squared plus chi minus 4 t cubed plus t to the 4th divided by 1 minus t all cubed. Right, and so this has got to be 2 minus 2k plus 6, right, and then plus qt in degree 1. Right, and so the thing I'm using here, I'm using that chi of OS is 1 minus q plus pg. Right, so the actual value here I get in degree 1 is pg. So it's not chi minus 1, it's chi minus 1 plus q. However, that's the only place that this q appears in the formula. Right, so most of the time I'm interested in regular surfaces. I don't know how to do anything at all with irregular surfaces. So I'm mostly going to do regular surfaces. So just assume that q is 0. Then chi of OS, the formula I have in my head, which is why I hesitated when I wrote down this, is pg minus 3. Right? So if q is 0 is the case I have in mind. Yes? And so let's do, for example, pg equals 2, k squared equals 1. This is a favourite, and a really old-time favourite. I don't know, it was certainly studied by Enriquez, and then by Kadara and Horikawa. And needless to say, Fabrizio. So if you think about it, the formula we're going to get is 1 minus t to the 10 divided by 1 minus t squared, 1 minus t squared, 1 minus t to the 5th. Okay? So let me do it just a bit more gently. So this is 1 minus t plus, so q is 0, I is 3. So this is 1 minus 6 plus 6 plus t squared minus t cubed plus t to the 4th. So this formula a priori does not necessarily have anything to do with generators of the ring, right? This is just a numerical way of representing all of this information about it's just this table. It's just no more and no less than this table of plurigenera. However, if we were hoping to put into this ring 3 generators in degree 1, then we're going to be sadly disappointed, because there are only 2 elements there. So when I was writing this down, I'm thinking, well, this is what it would be if I have 3 generators in degree 1, and oh dear, we need one. If I put in 3 generators in degree 1, then I need one relation between them. So that was just a mistake, right? So instead of doing that, let's do 1 minus t squared, right? And the effect of doing that is just to multiply the top by 1 plus t. Yeah? And so what happens if I do this? Anybody knows how to do? Anybody got a pocket calculator? This is 1, and then plus 0, and then plus 0, and then, okay, so it's 1 plus t to the 5th. Yes, and that this formula is equal to that formula. Right? I'm seeing 1 plus t to the 5th divided by 1, 1, 2. And so if I divide again by 1 minus t, if I multiply top and bottom by 1 minus t to the 5th, I get this. So this says take S to be S10 in P of 1, 1, 2, 5. So Enriquez and the old Italian geometers didn't have the use of weighted projective space, so instead they did something else. They said, well, let's look, in degree 1 I have this pencil of curves, PG equals 2, so, you know, here's my surface, S, and somewhere on it I've got this pencil of canonical curves. And because k squared equals 1, they have a single base point. Right? Now let's look in degree 2. So in degree 2 I have, so if this is x1, x2, y, z, then I've got x1 squared, x1, x2, x2 squared, but the next perigenus here is chi plus k squared, so it's 4. So I need one new generator here, y. Right? And so, you know, the effect of doing this is that I'm naturally writing down something which is a parametrization of the quadric surface in P3, the quadric cone in P3. Yes, and then the guys, so Enriquez, you know, was pretty good at using geometric imagination, so he says, well, what happens here is there's a quintic hypersurface here, intersection of P3 with intersection of this quadric with a quintic, and the map is a double cover of this quadric ramified in the nodal point here, and also ramified in this quintic curve. So the nodal point corresponds to this base point of the pencil. Yeah. And so this is a favorite example. This is basically the first example of a surface of general type. Right? So it's the only example which 5, you need to go, 4K is not birational. So it was studied, you know, by all of these guys in lots of different contexts. Okay, so let me make a remark about these formulas. So the remark is this. So there's 1 of 1 minus t squared. That's the rate of growth of the polynomial ring in 2 variables. So this looks like k of x1, x2. Right, if I take the Hilbert series of this ring here, it's 1 of 1 minus t squared. Right? And so the fact that there's 2 there is saying that this is going to be the Hilbert series of a curve. This 2 here is n plus 1. And the 3 there is telling me that I'm going to have a surface. And there's another number here that you can find, which is, let's add up all the coefficients in the top. Right, so if I do 1 plus g minus 2 plus g minus 2 plus 1, I get 2g minus 2. That's the degree. So this is the multiplicity of this ring. Right? The ring is a cone at the origin, and the origin has some multiplicity, and the intrinsic way of defining the multiplicity is in terms of these Hilbert series, Hilbert-Samuel functions. Yeah? And so here, you know, what's the degree? The degree is, what do you get if you add these numbers together? So there's 1 plus chi minus 4, minus 2 chi plus 6 plus k squared, and then chi minus 4. So all of this adds up to k squared. right? And in fact, I used this when I wrote down this formula, right? I didn't completely remember the formula. I remembered that these coefficients here, there's 1, 1, co minus 4, 2 co minus 6 are supposed to add up. Yeah? And so I want to do the higher dimensional case. So Riemann-Roch for a divisor D on non-singular, so on a n-dimensional manifold. So again, you're supposed to remember this formula, but it's a more abstract formula than the ones given before. So let me, the thing you're supposed to remember is integral over x of ch d times tod of x. Right? So this is a complicated business, and one of the main points of my lecture is really that we don't really need this. I'm going to work mostly with functions like this, which are just numbers, which are just where I can sort of forget about all this complicated stuff. But anyway, let me just give a kind of very brief introduction to it. So I've got x. So x, of course, is an algebraic variety, but it's also a topological space. So over C, he's a topological space, and so he has ordinary cohomology groups, x, with coefficients in Z. So this is analytic topology. So this is just a topological, so this is now a two n-dimensional real manifold. Okay. So a divisor or a line bundle has a first Chern class, or first Chern class of a divisor. Or this is also just written divisor class D, or just D. Right, so unfortunately this isn't quite enough. I'm also going to have to work with general sheaves. So F, a general coherent sheaf. Or general vector bundle, but, we're algebraic geometers, so a vector bundle is a particular case of a coherent sheaf. Right? And so this guy here maps to Chern classes, Ci of F. And the Ci of F belong to H2 of X with coefficients in Z. Right? And they satisfy a number of axioms. So I'm going to talk about this very, very quickly and just, dismiss it. So, but this is a very, very good topic for a student to study on his own or study in a seminar. And the place to study it is Borel-Serre, the theorem de Riemann-Roch, and Grothendieck appendix to it. So these papers, this is immediately after Serre's Fissure algebraique cohérent, so it's the late 1950s, and Grothendieck is telling topologists how they should define Chern classes and what the formal properties they have. All right. Anyway, in this formula, I need to tell you what Ch of D and what Tod of X are. And and what integrate means. So, so if I've got a sheaf F, then I'm going to write Chern of F. This is the total Chern class, right? And so this is C naught of F. So this is the rank of F. Am I just getting it wrong? I'm sorry, let me not worry about what C naught of F is, plus C1 of F. So this is now not in one cohomology group, but it's in all the cohomology groups at the same time. Right, and so what I'm supposed to do is factorize this formally. As, I think this one's always 1, product 1 minus gamma I. Yes, and so the gamma I are called Chern roots of F. Right? These guys here are called Chern classes. Right, and then, so we just write formally, this is factorized as gamma I. So this means that C naught is 1, and C1 is sum of the gamma I's, and C2 is sum of gamma I, gamma j. These are the elementary symmetric functions. Right, and so what this is just the thing you do in Galois theory. I think of this thing here as the coefficients of a polynomial, and then factorize a polynomial into linear factors. Right? We don't care who the gamma I are. The only place that gamma is ever going to appear is in these formal symmetric quantities. Right? So then the Chern character of F, this is the Chern character, this is just a definition. What am I supposed to do? I'm going to take the exponential of the gamma I. Am I going to multiply them together, or am I going to add them? Let's try multiplying them. Yes. So you know what we're really thinking. What we're really thinking is that the F belong to sheaves or vector bundles, and the natural operation is direct sum. Right. And one of the axioms for Chern characters of vector bundles is that when I do the product, when I do the direct sum of two vector bundles, the total Chern class of the direct sum of two vector bundles is the product of the two vector bundles. So here, in other words, here I have, this is additive, and over here this is multiplicative. Right? So I'd really like this just to be an isomorphism from K-theory of X into cohomology of X. Right? And, you know, if you want it to be an isomorphism, we're talking about an additive group there and a multiplicative group here. So that's why we take exponential. Right? And if I take the direct sum of two things here, that's supposed to map over here to the product of these expressions. Yeah? And so because there's an exponential map here, this is going into Q. Right? The exponential, so the Chern class of a divisor D, Chern character of a divisor D, is 1 plus D squared over 2 plus D cubed over factorial 3 plus and so on. It's just the exponential series where I write in D for the unknown, for the function. Right? So K naught. So K naught is the Grothendieck group of all coherent sheaves where the addition law on them is that when I have f primed goes to f double primed, this guy here is, in this group, is formally the sum of these two guys. Yeah? And the reason this is good is because if I'm calculating cohomology, whenever I've got a short exact sequence of coherent cohomology, I get a long exact sequence of cohomology groups. And so the cohomology here will be if I take alternating sums of dimensions to get Euler characteristic, the Euler characteristic of this guy in the middle will be just the sum of the two Euler characteristics at the end. And it just follows from a long exact sequence of cohomology, right? So the formula I'm interested in calculating there, chi of f, is a function on k naught of x. I'm writing it chi as a function of a particular sheaf or a particular line bundle, but it's really only interested in the class in k naught, right? And so, I would like to say, now that having done this exponential, I have an isomorphism. Well, I have to put rational coefficients here, otherwise I'm not allowed to write this down and so on. And so there's a whole lot of mess here. These things are not really isomorphic. They're sort of, they're different kind of invariants of x, with different language and different characteristic properties. But at least we have a map between the two now. Yeah. And so Todd of x. So x, this is Todd, the Todd class of the tangent bundle of x. So x is a manifold, so he has a tangent bundle. And this is an n-dimensional, a rank n complex bundle. Right? And to define its Todd class, what we do is the following strange thing. So again, I write down the total Chern class of Tx, right? And so I write this down as C0 plus C1 plus C2 plus Cn, and this is in H0 of H star of x z, right? And now I factorize this formally. So I write this as product of 1 minus tau I. Right, I equals 0 up to n. Sorry, let me call this little x. I'm sorry, it's just the one I have in memory. Right? And so, we don't know who the x's are. The xi, if you want to say that they belong to anything, they belong to some kind of extension ring of this ring. Right? So I make an algebraic extension, as in Galois theory, where I start off with a base ring, and I have a polynomial, and I introduce the formal roots of the polynomial over this base ring. So I'm in some ring extension there. Right? And so what we do here is, I'm going to write down the Todd class of x is product, I equals 1 to n, of xi over 1 minus e to the minus. So this is minus exponential of minus xi. So exponential of minus xi is 1 minus x plus xi squared over 2 plus and so on. Right? So this one and this one neatly cancel each other. So this is xi divided by xi minus a half. Right? So this is this term here, and I'm just sort of trying to make what I say next sensible. This is xi over xi minus xi squared over 2, and then plus other things. So let's cancel. So it's 1 over 1 minus xi over 2, plus other terms. Yeah? And so this is, when I evaluate this, this is just a product of formal power series. in principle going on forever, right? And so this is a product of, so it's 1 plus xi over 2, and then plus or minus, I should have prepared this. It's either plus or minus xi squared over 12, and then plus xi squared over 24, and then minus xi to the, I'm sorry. There's only one term here of odd degree. There's xi over 2 here, and then it's xi squared, and then it's minus xi to the 4th over 720, and then it's plus and so on. Right? So this is a slightly bizarre power series. I mean, those of you who've got a little pocket calculator could plug in and see, just plug this expression here into a pocket calculator, and you'll get out this, right? And these coefficients at the bottom here are called Bernoulli numbers. So they're magic numbers that appear in many branches of mathematics. So when I take this product, what I'm going to get is 1 plus 1/2 of sum of the xi. Right? That's the first term here. So imagine I'm taking this product. So there are n terms here. There's a product of n terms, and they're all power series going to infinity. But let's suppose that I only look at these first two terms. Right? Suppose I only look in the term of x squared, then I'm taking product of 1 times this 1 plus xi over 2. So each time, in each factor, I get xi over 2. So I get this. And this guy here is the first Chern class of x. Right? So when I wrote this down here, oh good. when I wrote this down here, the sum of the xi's is the first Chern class. Sorry, this mistake of sign is completely characteristic. Yes? And then it turns out that the next term is 1/12 of sum xi squared minus 2 xi xj. Right? And then plus and so on. Yes? And so what this is 1 plus the first Chern class of x, plus 1/2 of the first Chern class of x, plus 1/12 c1 squared plus c2. And then there's plus 1/24 of c1 and c2. And then there's plus 1 over 720 of some very long expression here. Long and complicated expression. So I can get out my notes and copy it out on the board if you want to, or those of you who have a pocket calculator can figure it out for yourselves. This involves things like c2 squared and c1 c3 and other terms. Right? And the main point I want to make is that there are 4 or 5 terms in here, and nobody has ever understood most of them. Right? And so these are terms which are fine for people who want to do theory, but in terms of calculating, nobody knows anything about them at all. And so, any theory that demands that you know C1, C3, and C2 squared and so on, we're just completely lost. We can never do anything. Yes? And so, think of this as a mysterious black box. And, let's keep it closed. Right? So, on the other hand, these terms are useful. These 3 terms are, this is what every algebraic geometer remembers and needs to remember. So this is minus 1/2 of the canonical class. Right? And so I told you there's this sort of characteristic error of sign happening. So the right way to define Chern classes is to say Chern class of the tangent bundle. right? So the canonical class is the top Chern class, the top wedge of the dual canonical class. And so its Chern class is minus this first Chern class. Yes? And you know, if x was a curve, the number that we're seeing here is g minus 1. Minus g minus 1. So this is the number 1 minus g in Riemann-Roch. Right? And this number here is called Noether's formula for a surface. Right? So Noether's formula says this number, chi of OS, this number I told you need to calculate when you're working in Riemann-Roch on a surface, this is equal to 1/12 of C1 squared plus C2. Right? And you know, people who do algebraic surfaces use this formula all the time. C1 squared is k squared, and C2 is the Euler number of x. The topological Euler number. Yes? And so this number here is minus 1/24 of kx times C2. Okay, so I've explained a little bit what this is and what this is. Right? So now I'm going to explain what this is. And let me explain it just by doing the calculation that I want to do on a threefold. Right? So on a threefold. So non-singular threefold x, and I've got a divisor d. Then what I'm supposed to, I'm trying to write out who is chi of OX of d. Right? D's a Cartier divisor on a non-singular threefold, right? And so what I'm supposed to do is, it says I'm supposed to write down 1 plus d plus a half d squared plus a sixth of d cubed. I'm supposed to multiply this by 1 minus a half kc plus a 12th c1 squared, k squared, sorry, kx squared plus c2, and then minus 1/24 of k times c2. Right? And so these classes belong to these cohomology groups. Right? And since I said threefold, it means that once I've gone beyond dimension 6, the groups are 0. So the power series just come to an end because there's no group for them to lie in. Right? And so what I have to do is calculate this, and then do this thing called integration over x. So it means that evaluate this product, and take the term in degree 6. So then it belongs to h6 of x, and with coefficients in Q, right? And then inside here, I've got the fundamental class, right? So this group here is isomorphic to Z, and this is the choice of a fundamental class. And as you'll notice, there's a kind of another of these characteristic contradictions. I really want this to be Z. I really want Z. And I'm not quite sure. Let me not worry about it. The number that turns up will be an integer, right? Because the left-hand side is an integer. Okay, so that was the program. Now let's do it. And so the thing you'll notice, I'm going to take 1/6 d cubed, and then I'm taking half d squared times k squared, and then I'm taking d times 1/12 of kx squared, and then I'm taking the last term. Yes? And most of these terms are homogeneous cubics in d and k squared. right? So if I write 1/12 of 2d cubed, right, that's that times that. And then there's minus a quarter d squared kx, so minus a quarter 3 d squared kx, right? And then there's d times kx squared, so he's already over 12, so all I have to do is write down d squared times k squared, right? And that's all. Yeah, so I've written down this term times this one, this term times this one, this term times this one, right? What's left? So plus, so there's 1/12 of d times k squared, sorry, d times c2. So why don't I write it all down together in one beautiful expression, 1/24 of 2d minus k times c2. Right? And so, you know, this expression here is 1/12 of d, every term here is divisible by d minus k, and 2d minus k. Yes? So the thing I want to, the main point I want to, well, I mean, you know, this is a, this is an integer. It's this number. So that's it. That's already the fact it's an integer implies things. So it implies 1/24 of kx times c2. I should have said this minus 1/24 kx times c2 is also equal to chi of OX. That's the Todd genus. It's what would happen if d was 0. Yes? So, you know, these are very special things, d and d minus k and 2d minus k, here and 2d minus k. And the special thing about them is that they're anti-symmetric. With respect to d goes to k minus d. Yes, and you know, I've done a, you know, I'm sort of taking, you know, like a magician taking this out of a hat, rabbit out of a hat. But you know, this we could have predicted in advance that this must happen. Yes, because Serre duality says hi of d is hn minus I of k minus d. Right? So I'm supposed to write dual to, and so when I take alternating sum, hi, and when I do minus 1 to the I, hi of d, I get minus 1 to the dimension of x times sum minus 1 to the I of hi of k minus d. Right, so in the present case, the dimension of x is 3, so this is minus 1. So if I did this expression, if I went through the whole rigmarole again with k minus d in place of d, right, I must get out exactly minus the same numbers. Okay? So this is basically the cue for my main kind of result, main kind of you know, point of view. It's not really a result. So I want to ask. So you know, for surfaces, so you know, curves. there's only one sensible invariant, which is the genus. Surfaces, as I've already said, there's k squared and there's pg, or pg and q. Right, but if Q arises, then basically I'm already dead. So I'm really thinking of surfaces corresponding to two values, k squared and k squared and pg. So surfaces, so threefolds. And then n-folds. So here